Good morning, everyone. So let me take a look on today's chapter. Is this topic multi-core. So this is going to be the second last chapter for this course. And you can look at that. We have another one. This is the final chapter for us to cover on this semester. And take a look on this. You can download, and I'm going to open from my prompt here. So for this chapter, we're going to go for multi-core, a little bit detail regarding on like previous chapter. In this book is cited from the chapter 18. From our module information is chapter 11. Okay, this is for today's topic. Let's check. So likewise, yesterday I did delivered for this one. You also can take a look on the yesterday recording. So when we talk about the multi-core computer, it's basically the architectures also has the kind of similar. It's also similar with the parallelisms mechanism. We talk about parallel processing last week. So this is continuously towards from the previous chapter. So we talk about the multi-core computer. In previous topic, we know about the single processor with a single data. And then we have a single, that is the first generation. Then we have a single processor with a multiple data can be executed one time. Then we have the advance of a processor manufacturing. Basically, we have a multiple processor. It means in that generation, the existing world used to have a concurrency of a computer processor. So we have more than one processor. And even single processor possible to execute multi-threads, or we call that the multi-instruction set. However, there are many of the challenges, like for example, as we discussed in the tutorial this week, okay, I have another one tutorial this week, which is this afternoon. So we had discussed about the challenges in the single processor and multiprocessor. For example, overheat, we have an interruption, how to handle the solution and challenge for the particular matter or issues. We also talk about not only about overheating, we talk about the dynamic scheduling. So that one is more towards to the detail during your practical class. I hope that our co-lecturers helping you on to brief and then do discussion together with you. So during this lecture, we're continuing what we had parallelisms mechanism in multi-core. Okay. Let me see the next slide. So if you look at to the next slide, I make it, I scroll. We have a category or a classes of the processor. First one is a superscalar, A. And then second, we have a simultaneous multi-threading, B. And last, which is what we have right now, multi-core. So we have a kind of these three of a processor. So you're going to take a look later when we're finishing this and during your practical class. Okay, what I want to talk about, all these three classes, you need to know. You know, right, in the final exam, we will cover this topic. And it's a type of a case study, kind of a questions. So I'm going to go one by one because we want to go for the one of illustration after this slide. So if we take a look on this one, we have superscalar computers. So basically, superscalar computers, we have only what we call one single processor. In that computer machine, one single processor. And I believe in your laptop right now, what you use for this architecture is all the current generation. I think the worst or general multitasking laptop specification nowadays is Intel Core 5. Like this laptop, my laptop, this is a company laptop. We're using Intel Core 5. It's just only able to do a kind of a general multitasking. Okay, I don't know yours, but maybe you have a Intel Core 9 here. That's the latest. AMD Ryzen, that is the latest. Basically, that one high spec. We call high-end computers. Based on my experience, I used to have highest spec, which is, they will cost about 14,000 ringgit Malaysia. There is a possibly have, I don't know if you have a higher spec now, there will definitely certain of purposes why you buy that laptop. Okay, so the higher spec we can classification, which is they can have the GPU, standalone GPU, graphic processing units. So we're going to talk about this, okay? So the first one, which is a super scale. In previous, we have a single processor, and only we have that processor possible to execute kind of the task, which is the task only a single instruction one time. And then to improve that the processor, the manufacturer come with an idea, which is why not? They will have a multiple of the instruction can be executed one time, but they are still sharing with one single processor, one single of a CPU. So that is the problem. So to solve that kind of a problem in terms of the heating, in terms of like delay, we talk about concurrency delay. So they come with a super scalar. That's what they call super scalar, scalable. If you want to compare in previous single processor with a single of instruction, definitely this is a better. So they come with the super scale. But still, single processor. So what they do in this single processor of the super scale, even it say it's scalable, you look at to the architecture on this, which is, okay, one single processor, okay, and they're able to execute multiple tasks. So you can imagine, actually I don't have a whiteboard here, you can imagine that one single processor, and then they will have what we call the CPU, okay, and then the CPU possible to execute many tasks. Like there is a box there, okay, there is a box here sequentially, and then only one single processor manage all, kind of that. What happened? Bottleneck, possible. Delay, also possible, but improve single processor with one single of instruction. But now many instructions can be executed, even using single processor. They're putting embed the design algorithm, how they're going to do this part. The features of the super scale, they will have first of all, the gist of this topic, they will have a multiple pipeline for each instruction. Okay, even single processor, they have multiple pipeline for that particular instruction. Next instruction, another pipeline. Another pipeline for another others of the instructions. So this is how it does this like in this architecture, super scale. So meanwhile, we will see what the performance focus is only focused to the instructions. Instead, single instruction can be executed, now many. So they just focus on that instruction set. When you have this kind of a design, okay, and you create another more pipeline, definitely there were traffic. There were traffic interparallelisms. You want to synchronize each of the pipeline because you want this architecture want to have like execute multiple of the instruction, focus to the instructions in one single clock cycle. So it's good, the idea is good, it's scalable, but definitely have a challenge. One of the challenge, second is, one of the challenge of a super scale, what do you think? When you open many of a pipeline, multiple pipeline, parallelism is okay, it's workable, but the challenge is it's too complex for designer to design that hardware components. So for today's topic, we talk about the hardware issue, about hardware performance, software performance in the multi-core. So that is one of problem when we have a super scale. Another problem is not only we have the designer need to create the complex of a component, the design of that algorithm to create the synchronization in terms of a pipeline, because we have a more than one pipeline now, with a many of a CPUs, many of a ALU units, many of a control units, all separately. So it's too complex. It's work independent. And the challenge, second challenge, is not optimum in terms of the speed of performance. Only one, the objective in the super scale, it's helping to reduce the time delay. It means they're helping to reduce the performance in the previous single scale of a computer. That's all. Because they focus only on that instruction. To have a multiple instruction can be executed one time. So they succeed, but this is a challenge. Complex of the hardware to be produced. Only to focus on instruction. Number one. Number two, they not only have a complexer design, okay. It's about the power consumption. Take a lot power density into super scale. And then we also have in the market, I don't know now, but in my generations, when I was a student, still young like you, okay, my generation, we have Intel Celeron. That is a processor, somewhere in the 1998. Somewhere 1998 until 2000, 2001, 2002, somewhere there. Okay, we don't have supercomputers, multi-core like yours. Okay, we only have Intel Celeron. They don't have the Intel series like you series. So we are using the first generation like this, number A category. Of course, lagging, one of the issue, slow, very slow. But for us, that time, that is the faster. That is the best. So that is the first of a category in this computer processor, super scale. Why they say super scale? Because they're able to execute more than one instruction in one single cycle or in the one time. Next, okay, two, to improve the challenges in the first category A, super scale, okay? So the designer and the provider think about, okay, how about we come up with another product? Instead, we have an Intel Core 2. You can see the trend, okay, to develop kind of architecture Intel Core 2 to Intel Core 3. It takes about 4 years. Because we need to also deal with the capacity of hardware, the chips, transistor, capacitors, and all of these chips is not easy to get previously. But that's why the generation will have a quite huge gap. It's not like nowadays, you see your mobile phone. I think Oppo, one of their smartphone, 9 months, 6 months have a new model. Okay, change a little bit the design of the algorithms, then produce new model within 6 months. 6 months compared to the 4 months, you can see the quality. iPhone now I think 17th, is it 16? iPhone generation 16. Why they come up with a 16? After how many years? Less than 1 year, come with one. Because we have a lot of the supply for the chips. Not only that, because there's people complaining, okay, it's easy to hit, easy. Because you open many of threads one time. Okay, we talk about that later. Okay, we talk about the second generation. The second generation is, they call it simultaneous of multi-threading. So, just now, the previous super scale have one CPU, okay, one processor, one CPU, not more than one CPU, and then one instruction, another instruction, multiple pipeline. So they said, how are we going to improve this? So we are lucky, okay, we have simultaneous. It means the burden from the multiple pipeline, bottleneck, and then heat and complexity on this hardware can be enhanced, all right, where that they are going to add more processor. So that's why you have multiple processor. Instead, the first one single processor, a same of architecture. Okay, they copy and they create another. So that's why you have another CPU, another single processor. Let's say we talk about that Intel Duo, okay, dual core, which is have more than one CPU, one processor. Previously, we don't have. The last, they have Intel series, which is Intel Celeron, single processor. Then they come up with we taking super scale, we copy and we create another chip, small chip, similar. So more than one processor. So you can see, like kind of the assignment we're giving to your case study, 6 hours of execution can be reduced to 1.5. Because of why? You have more than one engine. Okay? So we have more processors, same architecture, but only they add another additional components. In super scale, multiple pipeline, and then the overburden to the multiple pipeline reduce. You imagine multiple pipeline, one single processor, multiple pipeline. This instruction, another instruction, another instruction. So every of the instruction combined to be put into only one CPU, definitely overburden. So when you have more processor, same architecture, there will no burden. Less. It's not going to say not, but it's a less. At the end, what they do? Each of these instruction, they add another component. So you see single instruction, or single of a thread, they add another extra component to help reduce the workload of multiple pipeline. How they do? How they do? These additional components. In each single instruction, they put one single of a box chip. So this chip's box, basically, the function to handle the thread for every single instruction. So what is a multiple threads? We talk about multi-threading. What is a thread? Popular, which is right now, you are using the internet, you access one of maybe bank institution's server. So you are come from a different of a workplace or might be terminals. Okay, but you access same of a server. The protocol, the IP is the same. So definitely the web server management need to manage this resource. So many clients, okay, try to access and retrieve the server. This is multi-thread. Many clients, multi-thread. Distributions of a cloud computing system or access or resource also is one example, multi-thread. So it's a lot works to do for our processor. So that's why they need to have special, what we call special component, that check box, add in the every single instructions box. Only that, so they can do simultaneous execution, improve the current, which is focused to the instruction. Now they focus in the type of instruction, a type of threads. Imagine if you have a delay, overlaps, or might be interruption, so they're going to be giving a very poor situation to our processor. So that's why they add another single component. Another features for this SMT, basically, after the designer add that component, additional component, the box for each of instruction, they're sharing. Parallelly, this first processor sharing the resource for the second processor. Dual core, two core. Dual core is a two processor. So they share the resources, especially memory. In the previous, we only have a cache, one. And then we have a more processor. We need to work together, both of them. You can see the B illustration. What happens? To work parallelly, okay, while that too busy, they need to share the resources because they need to know which processor will do this thread. And other threads, they need to distribute equivalents. So this is what we have in the exercise. We talk about the work, what we call load balancing. And in here, SMT, very unique, which is they have an algorithm to handle that chip box of a multi-thread. Okay, they're using dynamic scheduling. So you're going to talk about this in detail. during your practical class. So they can do the balance and equivalence distributions of instruction and threads. Instructions are different, the threads also different. You need to read yourself for that. In previous, we have a L1 cache only. So when we have a multiple processor, to optimum the parallelism between the first processor and the second, if you have a 4 core, you have a 4 CPU. No, you have a more than CPU, but 4 processor. Okay, so this generation is Intel Core 3 and 4. If for AMD, AMD 2 and 3 Ryzen's, this one. And after that, to maintain the parallelism, to ensure that the performance of threading will be optimums, okay? So they need to have a load balancing between that. But they also have another advantage of this architecture, which is, they talk about the simultaneous just now, to execute the threads and the instruction, multiple of, what I call parallelly, multiple of a processor. If you have 4, so they said, sharing the memory to make it fast of the accumulator how? So they create different design of memory. Instead they have a 1L, level 1 of a cache, that's why we have in multi-core, level 2, level 3, level 4. So each level have their own single thread to be executed. So that is about simultaneous. But what is challenge in simultaneous? Just now we sharing, right? When the sharing conflicts, it's like you. What's your name? If you have a girlfriend, are you going to share your girlfriend with others? No, right? Yeah. What's your name? Okay, Jin Yun. Jin Yun is one of my student, my practical class student. Jin Yun, you have a smartphone. What is the model you use? iPhone 16, 15. iPhone, you see, iPhone, the problem, I think they come with a Pro and Max, right? Okay, which one the bigger? Max. Pro Max. Pro Max, bigger size. You know, bigger size, because I'm not iPhone user. Okay, that's why I just know this little bit less knowledge about that iPhone user. Okay, by using Pro Max. 15. Okay, the things about the iPhone, the size, right? The size, bigger bit, and then bigger and a small bit. Okay, iPhone, why they come with the 2 sizes? As I said to you, we talk about the cost of a user's want to buy, willingness to buy that. But there's a different, spec from the small size and the bigger size. But many people will go for, depends on their budget. Why they come with these 2 specs? iPhone is not water resistant. But the compact, you put inside the water should be no problem. But you see, because that compact, the heat, easy heat. That's an iPhone. Android, many of air circulation. So go put in the water, bang, your phone. So we'll see how that the chip, the board, okay, to be produced. But at the end, your smartphone, iPhone different architecture, is not this B category. Okay, it's not a SMT category. The iPhone actually is a combine these 3 category, not only 2, or not in the falling to the first or second or third. It's actually combinations of these 3. So in the simultaneous, because of the problem is a parallelisms, more processor, okay, multiple pipelines should be fine already, instead that previous of architecture. So they come with the problem, which is sharing memory. That's why we have a additional cache memory, Okay, instead that we have only one level, we have multiple level. Level 2, level 3. Now we have level 4. So this time round, they focus on only the thread. Then they're continuing, okay, enhance. So now you have i5, i7. Intel Core i5 and 7s. AMD Ryzen, also we have a 5, 7, 6 also we have. Okay, I think that one is about 2 years back, they came with that, which is the third category. So in the third category basically the features combination, the first and second. It means focus to instructions, set, execute more than one instruction, and number 2, focus to the threads. Okay, so there are combinations of these two. That is the last multi-core. But instead of have a dual core, 2 processor, they add another chipboard, which is they add another core. So that's why we have 4 core. We have a 8 core. 8 core, and more than that now, the latest, the best, high specification, which is what we have, more than 8 plus octal core, which is your smartphones. Okay, obviously that one for the online transaction processing, because so mess up. We talk about this complexity, it's not like this generation. So we released to number 3, which is C category. In the C category, we talk about multi-core. Multi-core means more than 1 core. Okay, it has both simultaneous multi-threading and also super scale. So we talk about this multi-core, absolutely. It's much, much better and super compared to super scale and SMT because the combination. Okay, so in multi-core, what happened when the provider, the manufacturer come with a more than 1 core, okay, more than 2, consider more than 2 core. So the issue here, they are not only focused on the instruction because already settled. That's not focused on multi-thread because that's already settled. They focus on to achieve optimization for all, which is focused on task sharing, organization of a task sharing in C. So this is the thing. When we have more processor, same goes like you. Now you have a many section. We have a total 543 students in this class. So we need to split to the many tutorial or practical classes. So to manage one by one, each of these sections, we have a different co-lecturer. And different co-lecturer with a different way, how they teach you, how they deliver the knowledge. Same goes like me too, one of it. So how to manage? We need to have a synchronization. Each of them deliver the same thing. Okay, and then how they're going to deliver depends on their way. So same goes in this multi-core. The problem, how to synchronize all the CPU, okay, preventing they don't have of kind of a concurrency problem. So in this chapter, okay, you're going to take a look later, next, okay, maybe next week we have a class before your short break holiday. You go to the next slide, you will see core coherency. So that is how the problem of that synchronization, okay, will be solved. Actually, we already know previous chapter. We already noted about the protocol. We have a directory protocol, Snoopy protocol, we have a massive protocol. So, number 1 category, super scale. In the final exam, definitely will have a question like this. Example, okay. What is the challenge? There are company, ABC company, okay, want to change the architectures, okay, or their server from super scale to multi-core, okay. And then they say, explain what are the challenges of this transformation, kind of a question. So you will say the challenge of the super scale can be solved by multi-core, example. So you need to know the challenge in multi-core too. giving example of the failure of implementation in multi-core. So you will say, oh, one of a challenge is about interruption, the threads, just giving one thread. And then that is an example, and what is the solution? So that is of a kind of a pattern in our final exam. So we have each of the types, and then there are the features of that types and the challenge in terms of hardware. So we talk about in multi-core, not quite difficult in terms of the hardware. Of course, they will have a challenge, but they were more towards to the software, how they want to have maintaining the optimum of the dynamic scheduling, one of example. And we have more, okay? All right, I have not much time to cover this. So, yeah, one thing that I want to ask the students, if you understand this, okay, look at to this graph. If you understand, I said. This graph. We have understand that we have a three type of the processor, which is one is super scale, single processor, but they're able to process multiple instruction. So the focus in the instruction issue happens in terms of hardware, not the software. Then it's been enhanced by SMT, simultaneous multi-threads, which is focused more to the thread, enhance the instruction problem and multiple pipeline. And next we have intercore 5 and above, like a Ryzen. So we understand that SMT, combination SMT and also super scale processor, you not only can do the general multitasking job, but this computer, it's helping us to do some of that editing, enhancements on that advanced multitasking. For example, if you want to do online transaction processing, but it's so considered not efficient. But if you have more core, definitely more faster. So this is the issue in terms user demand. User demands that I need to have a higher speed. Okay, so higher speed, you need to have a higher spec. And we have another one term of a computer processor, we call that high-end spec. High-end spec, I mean the one that I said just now, 14,000 ringgit Malaysia, which is they have a GPU. But before we go for that, this illustration, did you understand? Did you understand this graph? If you do not know, then you say, yes, I do not know. Easy, right? You do not know. Did you understand about this illustration? We have axis. Yes, thank you. No, I just starting to explain about this. Did you understand about this? No. Okay. There? You don't know. All right, no need to ask that, definitely. So you mean you not to do revision for this chapter? Never mind. So let me see. This is basically number of processor. You can see this illustration is about the speed up with a 0%, 2, 5, and 10, okay, of the processor. We have a x-axis. So the x-axis is about the number of processor. We have a first one processor, next two processor core, 3 core, 4 core. So they increase, okay. I mean it's increased from the from a one, only one processor, go to they have a 2 processor and 3 processor and add up more increase. And the y-axis you see speed up. They say speed up. It means time, interval time they take to execute that propagations of sequential of the instruction. So we know, if let's say you're giving 3 instruction A, B, and C, one time, you ask the processor to execute. So definitely it's still in sequence. So this is what we call sequential propagation for each of the instruction of data. So this what we call propagation of instruction, okay, is a per time speed, okay. They have a formula for this one. They call that is a relative speed up. So you see the first one, the first line is very straight, 0, Second is a 2%, 5%, and 10%. You see, why? Okay, even the highest spec, multi-core, which is octal core, is the highest compared to others, which is only 1 processor, 2 processor, 3 processor. But the speed getting lower, 10% is dropped. What happened? Suppose it's the highest spec. It means the speed must be faster compared the other one, lower spec. So there is a significant why I highlight about this graph or this illustration. High spec, but slow. Look at to the 0%, okay? With balancings of the, what they call cumulative segmentations of instruction equivalence to be given, okay, equal to each processor, all right, the speed will be increased if balance, the balancing, okay? That's why there's no problem, 0, no issue. But when you see the propagation of this instruction segment, okay, burden the processor, although the processor is a high spec, more than 3, more than 4, more than 5. Even here we have a 6, 7, and 8 core, they lose the speed and slower. And when you push your computer, all right, to process more, even more over of the thread or instruction, they're going to lose the speed and getting slower, even though you have a high spec. So if you have an iPhone 16, doesn't mean that iPhone 16 is better than iPhone 11 or 10. Okay? It's only will solve, each of model come to the industry or to the market to solve simple and single problem only. Per my understanding, iPhone 16 just want to solve the overheat. And then they charge you more than $500 and you buy. So think wise when you want to buy that certain of the model. So what we learn from this illustration, how good the core, even more, okay, more core, all right, the speed have diminished. What I mean, they have a limit in terms of a speed. But if you push, definitely they can go. So the higher processor also will be burdened. Even you have sophisticated algorithm for that particular multi-core. Same goes like human. You being push, you burn out. So this is showing to us processor even high spec, but if you push a lot of threads, the speed will be getting slower. So far now, even Intel Core 9 and AMD Ryzen 9 facing this problem. Okay, so I always ask my student, smartphone especially, why slow? Miss, I want to know why is it slow, what is the issue? Did you do the cleaning? I asked the student. I do cleaning, I transferring all the images and data to my hard drive, but not so like 1 month only one time. Okay, I mean not proper cleaning. I said, so do I need to, to put in some of improvement into my my PC or the smartphone? Actually, he asked about the smartphone. You want to add the RAM, memory, you want to improve the RAM, the memory. You know, the cost you want to improve the RAM, actually same like you buy the new phone. I said. So, okay. So what you need to do, because it's overheat. iPhone 11 or 10, if I'm not mistaken, he used that. It's overheat, hot. Within 1 minute, hot, he said. So he's worried the phone is burned. But, okay, blackout. The phone also can black out. So I said, like, what you need to do, always clean the memory. Okay? Oh, I want to buy iPhone 16 because iPhone 16 put the chip, which is the function like a fan in the laptop, the board. Doesn't work well. Tell you the truth. Okay? It doesn't work well. So, you're going to do the study about this one. This is one more, okay? Even we have a massive protocol. It's like a curving, okay, wave in this higher processor. But in this case, what the difference between previous illustration? This is when your computer machine processor overheat. They said it overheat. Actually, it's a heating. Okay, same go your smartphone. That's why it cannot lasting. 1 or 2 years you use, you need to buy a new one. So laptop, always, if there are users, I don't know, they don't like their laptop or what. They don't keep nicely the laptop. You on 24/7 your laptop, okay? But if you use a fan, should be fine, okay? So this is when overheat, okay, inconsistent. The graph is not consistent anymore. And next, for this chapter, actually there's a lot. Obviously cannot be actually covered by only 1 hour. After we have multi-core, okay, it start have a cloud computing. Where we start at 2003, start the architecture. And many API, okay, many API, different platforms. Some use Mac, some of using Microsoft, some are using Linux, different platforms. Oh my God, variety platforms. So they come up with solutions, okay? Why not? All right, the type of thread just now, we split the work tasks. So I think that is the programmer and the manufacturer think of. We split the task, okay? It seems like the question I'm always do in my practical class, question 1, this group do. Question 2, that group do. So it seems like, I segregate, distribute the task. So this is the way how they think, maybe, I don't know. But we have the most latest. We call heterogeneous multi-core processor, this one. Okay, that's what I put into this slide. Okay, if you look at that, we have a multi-core, core. Okay, more cores, more CPU, more ALU units, more control units, all more. Sharing together the resources, bus also share. Okay, is that good enough? No, still not good enough. So this is what we call high-end computer architecture. High-end, the best we have. Then you have virtual memory. Now you can have virtual memory. You can do mirroring, share. So that you have a cloud to share all the information, sharing the cloud, mirroring that storage. We call that heterogeneous multi-core. It means that manufacturer come with a GPU. So what's the difference between this architecture with the multi-core architecture? So we talk about multi-thread just now. The thread can be a lot. Okay, instruction set can be different. Okay, computational, definitely normal computational like the maths, formula. I guess that our core or even single processor can execute. But the thing when they come in our life, in the world, the term of AI, artificial intelligence. So nowadays, AI is popular. If we talk about 2011, nobody knows, only a few knows about AI. So AI required the data crowdsourced from you. That's why Google, okay, Google Chrome, that's the best browsers. Everybody Googling, using that Google browsers. Not even use Safari, Flux, and so on. Because of, from the one that you input into the internet, they're going to store the data and they create the prediction. From that prediction, they take advantage, which is we can do analysis and helping students or users, others in businesses make decision. Okay? I've been in the AI in 2009. This field, it's really new for me. AI, what is the AI? That time, one of a pioneer I need to work with my teams about AI. Now AI very common. So when you do the prediction, especially nowadays, you see the television, TV. Okay, you have a high definition, smart TV even. Not about the size, I talk about the clarity, okay, the clarity of the pixels, the picture and video. So we talk about multimedia application and about rendering. Normal computer like multi-core cannot do this, okay, because it's require a lot of memory. And then calculation, additional calculation. Like you want to do the rendering, 3D image, okay, has a shadow. There is a formula to do that. So the normal CPU cannot do computational, this exclusive and advanced computational. Cannot. Only special component, they add GPU, graphic processing unit, can do this advanced computational. If you learn about AI, maybe your major is in artificial intelligence, other friends doing that, they know about this. They need to calculate frame by frame. We talk about the video. You want to cut the video from your WhatsApp, you want to send to other friends or relative. You want to cut the video, it takes about buffer time, right? Maybe less than 3 seconds or 5 seconds, because they do rendering. Who's doing this? GPU. Normal CPU, normal CPU or normal processor unit can't do that. So to have this advance of a cloud computing distributed network and AI, which is possibly to calculate and compute kind of instruction required image processing, we need to have a CPU. So they came to come with like, oh, there are many people, which is gaming also one of the good businesses, okay? But you see, you need to always update, okay, your resolution, the screen resolution. So this is the problem. Then if a normal smartphone or computer, you're lagging. You want to enter the game, possibly taking a lot of time. So based on my experience, my study is a neurofuzzy logic. I need to predict 4,000 of a student data, 4,000, each of that for 2 years. So imagine I only have a normal computers to do analysis, cannot run. I'm using MATLAB, only that software, cannot run. So I go to my universities, and then my university have advanced labs. Okay, they use Mac. So then I see like, oh, this is super and of a computer. But still, from every Saturday 3 times, I came to my university to do analysis, just want to analyze the data, to do prediction using MATLAB. You know what? From normally I take 9 to 10 o'clock until 7 to 8, every Saturday 3 times, you know, done. Take 3 times. Okay, I mean 3 days, whole day to do analysis. Very slow. And then how many of PC? 21 PC. So imagine how slow is that. That about 10 years back. Now you have this GPU. If your laptop have the GPU, you install, okay, separately the GPU, definitely your laptop is superb. It's the best laptop, I guess, high-end. Power specification is quite the power optimums, okay? And then possibly no delay. My one, which is the one that my company gave to me previous, that I said 14,000 is AMD Ryzen. Okay, that one I want to turn on. Okay, I just turn on the button. I just press the button. Less than 3 seconds, pop. The OS already pop up. So that fast, you know. But still, I said the speed has a limit. So we understand 4 types of the processor. Okay, so we're going to do the case study about these processors. In the final, we have this question about multi-core. Okay, we're going to highlight. I'm going to inform the other lecturers what we're going to highlight on this chapter. Okay, wrap up. I'm done. Attendance.